Okay, so I'm getting lots of questions about this modelling task. I'm just going to clear all this. So I just wanted to go through it real quickly, just hopefully clarify and give you a chance to pause, go over whatever's most relevant to you. Okay, so reading this question, modelling task, when a ball is thrown, the model of its path is y equals ax squared plus bx plus c. So we know it's a quadratic, and this is what we're using for our quadratic unit. So y is the vertical height in meters, and x is the horizontal distance in meters that the ball would travel from when they're thrown. A, B, and C are constants. Okay, so what we're going to get is we're going to get an actual picture, a real-life picture of what is happening, the path of this ball after it's being thrown. So first question is we're given a model, this minus 1 over 8x squared plus 5 over 4x. On the diagram, sketch the graph of this equation. Okay, so we're going to want to grab our calculator. No, we're not. We're going to want to grab our graph, and we're going to try and graph this. Now, one of the things I always quite like to do is to make it look exactly like it is in the question. So I use this control and divide to make it minus 1 over 8 x squared plus, and again let's make it as a fraction, 5 over 4, whoops, I've missed it, 5 over 4x, and there it is. Now it asks us, if you look at the domain, what we're interested here is the values from 0 up to 12. So what does that mean for us? Well, I think it's probably worth just changing it on our axis, and I'm probably going to go minus 1 just so I can still see what's going on, but I need to make sure I go up to 12 here. And so we can see this parabolic shape. We don't have an indication on our y-axis how high it needs to go, but we've got that parabolic shape, and it's important that it cuts before the 12, because you can see the 12's here and this cuts back down before the 12. So that's the things that they're going to be looking for. So we're going to start at 0, make that beautiful U shape, and hopefully I'm going to duck down just before the 12. I'm not especially happy with that. I might just try again. Wasn't really watching where I was going. Always watch where you're going when you're doing a graph. And I've done it again. There we are. It's ducked down before the 12, so I'm quite happy with that. Onwards. How far does the ball travel horizontally before hitting the ground? Well, that's going to be how far does it go this way, and effectively what is that coordinate there. So we can get our GDC to do this for us. We want to analyse the 0 between here and here. There should be 1 and it's at 10. So I can, well, I don't need to write it in there, I can put it in here, 10 meters. Greatest height that the ball reaches. Okay, so again on my GDC, menu, analyze graph, I want the maximum, and what's the maximum value between here and here? Well, it reaches a height of 3.125, so you've got to give it the context that we're after the y coordinate here. So that is 3.125. M's. A vertical fence 2 meters high stands on the horizontal ground 6 meters from where the ball was thrown. So that means at 6 meters, there's a fence here 2 meters high. So that's 2 meters high, 6 meters along. That's what this is saying. The question is, how far above the fence is the ball? So what I would look at here is the table of values. So Control and T. We know it's at 6 that we're interested in, because it's 6 meters away, and the ball will be at 3 meters in height. So the question's asking me, the fence is 2 meters high, how far above the wall will that be? Well, that would just be 3 minus the 2 meters, that equals, do that for you, 1 meter. Okay, there are 2 positions with a 2 meter high fence could be built so that the ball passes just over the top. One of them is 2 meters away. We can see that here, 2 is 2. X value of 2 gives us a Y value of 2. What's the other position? So what it's saying is it's looking for this second output of 2, which we can see happens here at 8. And the other position is 8 meters away. Okay, the ball is now thrown from 1.5 meters above the ground. Use this information to modify the model. So if we're throwing it, same idea, but everything's moved up 1.5 meters up. So we just need to add on 1.5 meters to the model. So write out the model again, which was So get minus 1 over 8x squared plus 5 over 4x, and now we're going to add on 1.5 to that. Okay, question 2. Second ball is thrown from 0, 0. It passes through the points. Okay, so we're no longer going to have this thing on for this next question. Passes through the points 3, 1.2 and 5, 0. Use the coordinates to write down 3 equations in A, B and C. Okay, so what we're interested in, if we remember back to the start, is y equaling ax squared plus bx plus c. And we're going to use the 3 points. So at 0, 0, what happens? We're going to get y is 0, x is 0, b is 0, and c is just left there. Ah, lovely. 0 equals c. That's quite a nice equation. Now, we can do the same thing for 3, 1.2. So x is 3, y is 1.2. So 1.2 would be equal to, now I'm squaring the x coordinate, so 3 squared is 9, 9a, plus 3b, I already know c is 0, so we've got a second equation. 1.2 is 9a plus 3b, that's like a 36, doesn't it? 3b, and then finally at 5, 0, now x is being squared, y is 0, x is being squared, so x is 5 squared, 25, lots of a, plus 5b, and that's it. So 0 is equal to 25a plus 5b. Marvellous. Okay, what we got then? Solve your equations to find the values for a, b and c. I already know one of those. Write down your equation of the path of the second ball, and write down, okay, so I reckon I'm going to get my calculator to do this for me, since I've got it set up and ready. So let's get it solve these simultaneous equations for us. So let's insert a calculator. We're going to get it to do some algebra for us, so menu algebra. And we're going to solve a system of linear equations. We've got 2 equations, which is these 2. And although my variables are x and y, whereas on here they're a's and b's, I'm just going to write them in terms of x and y's instead of a and b. Just easier for me to just read it off, and I'll just continue to be in alphabetical order. So I'll change a for x, b for y, and then change it back again. I don't know why I do this. I could easily change it for a and b, but it's just habit and just make my life a little bit easier. So the first one is 1.2 is equal to 9x instead of a plus 3y. And the second equation is 0 is equal to 25a plus 5. Oh, I've done it wrong, haven't I? 25x plus 5y. Solve for x and y, hit enter, and we get our first value. It says x is minus 0.2, but in fact that's an a, so minus, whoops, let's get a pen. Minus 0.2, and b is 1. So that means the equation y is equal to minus 0.2x squared plus an x, and that's it. There's no c value. I don't need to write it on the end. Okay, part C. Vertical fence 2 meters high stands on the horizontal ground 2 meters from where the second ball is thrown. Will the second ball hit the fence? Explain your answer. My plan for this would be to see the graph once again. So we're now interested in minus 0.2 x squared plus x. Okay, so we've got this nice graph going on, and what we're interested in is it's 2 meters high and it's 2 meters away. So I'm interested in what's happening here at x is 2. Again, control table of values. When x is 2, we get a y value of 1.2. So the answer to the question, will it hit the fence? Yes. Because the ball is only 1.2 meters high. Okay. Ball is thrown from 0, 0. It passes over the fence k meters from 0, 0 and hits the ground at capital X0, okay. General model for the path is this. H is the height in fence in meters, okay. X is the horizontal distance in meters that the ball travels before hitting the ground. Okay, there was a little clue on that second bit here. Using this information from 1A, show that the general model gives you this, right. So this looks like what we started with, but what we need to do is piece this together. Now don't get overwhelmed by this notation, H's, the K's, the X's, the capital X's. Let's just write down what each of the things are. So what I'm looking first is, what's this H? H is the height in fence of the meters. So if we recall back, H has always been 2 so far. We can look back at it. And that's this, 2 meters high, that's where that's come from. Next one then, we've got a capital X going on. X is the horizontal distance in meters before touching the ground. That's this answer, that's 10. And a K value as well, we need to work out. What's K? K is, it's going to tell me somewhere, passes over a fence K meters from 0, 0. Okay, so that is how far away is the fence. That's this one, and that's going to be, no, that's 2 meter high fence, position 2 meters from where the ball was thrown. It's this 2 here. It is a 2, but it's that 2 there. So K is also equal to 2. Let's plug all that into this formula, and we've got Y is equal to 2x, x minus 10, divided by K, 2 minus 10. So that's just putting in all of the values that we've got. Let's just have a look at what we've got. That's, let's go down, equal to 2x squared minus 20x divided by 2 times minus 8 minus 16. So that's equal to 2 over minus 16x squared minus plus 20x over 16, and my fractions should cancel to minus 1 over 8 x squared plus 5 over 4 x, and we've got the answer that we wanted. Beautiful. So don't worry about these if they look intimidating, just piece it together one by one. Crucial bit for this, I think, unlocking this question was perhaps looking at this thing in bold, making sure you're dipping back to that point. Okay, how are we doing? I've got a few questions to go, and then we'll be there. Explain why the general model does not give the equation of the ball's path in 1b. Okay, let's look back at 1b. So that was when it was now 1.5 meters above. Okay, so that's going to be what we're going to have to write in something like this. So for part B, it would have no longer starts at 0, 0. Something along those lines we're looking for here. Okay, a ball is thrown from 0, 0. It passes a 2 meter fence, 8 meters from 0, 0, hits the ground at 12, 0. Use the general model to find the equation. Okay, so we need to use this model again. Okay, so H here was what? H was the height in fence of the meters. So H is equal to height in fence 2 again. Okay. X, capital X, hits the ground. So capital X is now 12. And K is the K is what? K was what? Fence of K meters high. No, I've got something wrong here. H was the height of the fence. Oh, sorry. So K is the distance away. So K is now this value 8. Okay, let's plug all these values in. We should get Y equals H X. Then it was X minus X, 12 in this case, divided by K, which is 8, multiplied by K minus X, K minus X, 8 minus 12. And we can expand and simplify this. Not easy in this space, is it? What have we got? 2x squared divided by, what's this down the bottom? It's going to be 8 times minus 4. So it's going to be minus 32. Plus, because it's a minus, 24x, again over I've sorted out my negatives already, again over 32, which is going to simplify to y is equal to minus 1 over 16x squared plus 3 over 4x. Okay, find the position where another 2 meter high fence could be built so the ball just passes over the top. Right. Let's have a look at this. So I would again plot this and see what's happening. So we're going to graph this, and I'm interested in minus 1 over 16 x squared plus 3 over 4 x. Okay, and we'll go straight to our table of values because we're interested in where the 2 meter high fence is. So we were given one at 8, which is here, you can see, and you can see we've already scrolled past one. So the other one is at 4. Okay, see then, a ball is thrown from 0, 0, it passes just over a 2.5 meter high fence. The fence, two 2.5 meter high fences. The fences are built so that one is twice as far from 0, 0 as the other. Well, we've seen that already, that kind of happened here, didn't it? From 4 to 8, and even on the previous one it was 2 and 4. So that seems to be what's happening anyway. One fence is 10 meters from 0, 0. Find the possible horizontal distance. I've lost my cable. Come back, it's here. Okay, right, so the piece of information that we're getting is we got a 2.5 meter high, and that's 10 meters away. Now, the way that I would visualize this is this can happen at 2 possible instances. We could have a quadratic that does something like this. Doesn't look great, does it? We could have a quadratic that does something like this, or we can have a quadratic that does something like this. Okay, so that 2.5 meter high fence could be the first fence on a wider quadratic, or it could be the second fence on a shorter one. Now, in order for it to have symmetry and be twice as far away, we know in a quadratic there's always going to be that symmetry around the vertex. So this would have to be, well, that would have to be 5 in order for that to be 7.5, and these are to all have that symmetry. So 5, 10, that's going to be at 15. Now, in order for the second one to work, that 15 is going to be relevant again, but I think we're going to then hit at 20 to then go down at 30. So what's the question actually asking? It's asking us the 2 possible horizontal distances the ball can travel. Well, that would have been this 15, or it could have been this 30. Okay, find the equation for each path of this ball. Okay, so we need to simultaneous equations again. Now we're going to use the coordinates that we've just established. So one is here, which is at 10, 2.5. And then there's another one here at 5, 2.5. And that's got to fit ax squared plus b. So equals y. So at the point, what was it? I said 5, 2.5. And then also, well, let's do this one first. X is 5, so it's going to be 25a plus 5b equals 2.5. Y is 2.5. Then also at 10, 2.5, I'm going to have 10 squared, 100a plus 10b, that also equals 2.5. Now we're going to have the same thing going on in the second possibility. This coordinate is shared, but then we're going to have the second one at 22.5. So that's going to be at 22.5. That's going to be 20 squared 400A plus 20B equals 2.5. Now there's going to be one that's shared by the two of them. So the 2.5 is going to be shared by both this solution and this solution. Okay. So I might get my calculator to do it once more. So that was on the calculator. We're gonna, no, not dot. We're gonna get it to do some algebra for us. Linear equations. Let's change it to A and B this time. So we've got 25A plus 5B, 25A plus 5B, and that was equal to 2.5. We've also got 100A plus 10B, and that's equal to 2.5. Okay, so I'm getting my first equation with an A value of minus 0.05. So y, whoops, that's not very neat. Y is equal to minus 0.05, minus 0.05x squared, and b is 0.75, so plus 0.75x. Now for the second one, now I need to use this, don't I? I need to go back to my calculator. So let's go again, menu, algebra, solve a system of linear equations 2. Let's do it in B again. It probably does stop us from making some mistakes. So linear solve here of, again, we're going to, that shared one was 100A plus 10B is being equal to 2.5. And then the other one was 400A plus 20B, that also equals 2.5. And now I've got an A value of minus 0.0125. So y is equal to minus 0.0125x squared plus, now my b is 0.375x. Okay, what is the greatest height that the ball reaches? Okay, let's plot these two again. So let's insert a graph. Okay, f4 of x, we've got minus 0.05 x squared plus 0.75x. First option, the ball might travel, and then the second one I can insert by pressing tab, and that's minus 0.0125 x squared plus 0.375 x. That's this option. Let's make this a bit larger. I can't get it. Okay, here's something. What I might do is just move this out of the way. Should be able to get my axis. It's here somewhere. This is where it gets a bit fiddly. Okay, if we can't do it, then we should be able to do window zoom, Windows settings, and I want my x to be increased from 60. Maybe let's go 25. Still not huge, is it? Right, let's just see the height of these though. That's what we're interested in. What's the maximum height? So the maximum value for the pink one is 2.813. And then analyze graph, and maximum value for the green one is 2.813. My goodness, what are the chances? I was thinking as I was doing this, which one is it referring to? Let's just have a look at both. They're both the same. Jolly good. That helps me answer that question. So what's the greatest height the ball reaches? 2.813 meters. And that's us done. Hopefully that's quite helpful, show you how we can use and utilize the GDC for this modeling task.